Hello, I'm Austin Mallier, and I've chosen 7 problems for the first midterm for Physics 270 of the spring 2020 semester. And I've chosen 7 problems from the first 7 chapters to demonstrate my skill and knowledge through the first weeks of the term. And for the first problem I picked was problem 1, number 42. And the problem reads, the average density of the planet Uranus is 1.27 times 10 to the third kilograms per meter cubed. The ratio of the mass of Neptune to that of Uranus is 1.19. The ratio of the radius of Neptune is 0.969. Find the average density of Neptune. So I wrote the ratio of the mass of Neptune over the mass of Uranus, which is equal to 1.19, and then the radius of Neptune over the radius of Uranus, which is 0.969. And I use the definition of density equation, where the density is equal to the mass over the volume, where volume is 4/3 pi r cubed for spheres, and we're assuming that the planets are spheres. We know that the density of Uranus is 1.27 times 10 to the third kilograms per meter cubed, so I compared the densities of Neptune and Uranus, which gave me the mass of Neptune over the mass of Uranus times the radius of Neptune over the radius of Uranus cubed, which is then equal to 1.19 times 1 over 0.969 cubed, which then gave me the number 1.3079. I then used to find the average density of Neptune. I used the given equations, which was then 1.3079 times 1.27 times 10 to the third kilograms per meter cubed, which gave me 1.66 times 10 to the third kilograms per meter squared, or cubed. And then for the second problem, I chose problem 21 of chapter 2. And the problem reads, a particle moves along the x-axis according to the equation x is equal to 2 plus 3t minus 1t squared, where x is in meters and t is in seconds. At t equals 3 seconds, find position, velocity, and acceleration. To find the position, we evaluate the given expression. To find the velocity, we differentiate and then do it again for acceleration. So for the position, all you had to do was plug in the 3 seconds into the equation, which gives me 2 meters. Then I differentiated the problem, which gave me 3 minus 2t, and plugging in 3 again, I got minus 3 meters per second squared. And then I differentiated again, and that gives you negative 2 meters per second squared for the acceleration. And then moving on to problem 3, I chose problem 36, and the problem reads, given the displacement vectors A equals 3i hat minus 4j hat plus 4k hat meters, and B vector, which is 2i hat plus 3j hat minus 7k hat meters, find magnitudes of the vectors and express each in terms of rectangular components. So I used the law where C vector is equal to A vector plus B vector, and I added the vectors up and got the magnitude of 5.92 meters. And then for B, we were told to find 2a vector minus b vector, and I did the equation, and I found that the magnitude was 19 meters. For our chapter 4 problem, I used problem number 50, And the problem goes, a river has a steady speed of 0.5 meters per second. A student swims upstream a distance of 1 kilometer and swims back to the starting point. Find if the student swims at a speed of 1.2 meters per second in still water, how long does the trip take? B, how much time is required in still water for the same length swim? C, intuitively, why does the swim take longer when there is a current? So the total time interval is the longer time plus the longer time swimming against the current plus the shorter time swimming with the current. I use the equation T equals D over V will be used, and then for A, I use the time upper, which is 1,000 meters over 1.2 meters per second minus 0.5 meters per second, which gave me the number 1.43 times 10 to the third seconds plus 1,000 plus time down, which going down the stream, 1,000 meters over 1.2 meters per second plus the 0.5 meters per second, which gave me 588 seconds. So time total would be 2.02 times 10 to the third seconds. B, the total time in still water, I used 2,000 meters for both distances, down and back, over the speed, which is 1.2 meters per second. And that gave me 1.67 times 10 to the third seconds. And for C, I said it is harder to swim against the current because it is a harder challenge to swim against it due to the added force going against you. For the chapter 5 problem, I picked number 33, and the problem goes, a bag of cement weighing 325 newtons hangs in equilibrium from 3 wires in figure 5.33. 2 of the wires make angles of 60 degrees. Two wires make angles theta equals 60 degrees and theta 2 is equal to 40 degrees. Find tensions of T1, T2, and T3 in the wires. And then there's the figure right there. For the equilibrium of the sac, T3 must equal Fg, which is then equal to 325 newtons. And then I found the sum of all forces in the y direction for the knot, which gives the equation T1 sine theta 1 plus T2 sine theta 2 is equal to Fg, and then the same thing for the x, but with cosine. And then I eliminated T2 by using T2 is equal to T1 cosine theta 1 over theta 2 and solved for T1 and got the equation Fg cosine theta 2 over sine theta 1 cosine theta 2 plus cosine theta 1 sine theta 2 is equal to Fg cosine theta 2 over sine times theta 1 plus theta 2. And then there is the T3, which is equal to 325. I plugged in the values for T1, which would be Fg times cosine 40 over sine 100, which gives you 253 newtons. And then T2, plugged in T2 back into the equation and got 253 times cosine 60 over cosine 40, which gives me the 165. And then for problem 6, or for chapter 6, I use problem 29, and the question is, calculate the force required to pull a copper ball of radius 2 centimeters upward through a fluid at the constant speed of, I didn't put in the centimeters per second, take the drag force to be proportional to the speed with proportionality constant at 0.95 kilograms per second. Ignore buoyant force. Since the upward force velocity is constant, the resultant force on the ball is 0. Thus the upward force applied equals the sum of the gravitational and drag forces. The mass of the copper ball is equal to m is equal to 4 pi times the density r cubed over 3, which is 4/3 pi times 8.92 times 10 to the third kilograms per meter squared, meters cubed, times 2 times 10 to the negative 2 meters cubed. Then the applied force is then F is equal to mg plus bv, and that is 0.299 kilograms times 9.8 meters per second squared plus 0.95 kilograms times 9 times 10 to the negative 2, which then gives you 3.001 newtons. For chapter 7, I chose problem 20, and the problem goes, a light spring with constant 1200 newtons per meter is hung from an elevated support. From its lower end hangs a second light spring, which has spring constant 1800 newtons per meter. An object of 1.5 kilograms is hung at rest from lower end of the second spring. A, find the total extension distance of the pair of springs. B, find the effective spring constant of the pair of springs. So the same force makes both light springs stretch. So solving for A, I had x is equal to x1 plus x2, which is equal to mg over k1 plus mg over k2, which is then equal to mg times 1 over k1 plus 1 over k2. And then that gives me 1.5 kg times 9.8 meters per second squared times 1 over 1200 newtons per meter plus 1800 newtons per meter, and that gives me the answer of 2.04 times 10 to the negative 2 meters. And then for the effective spring constant, I use the equation K is equal to F over X, which is then equal to mg over mg times 1 over k1 plus 1 over k2, which is then equal to 1 over k1 plus 1 over k2 to the negative 1. And then I inputted the values and found 720 newtons per meter.